All right, welcome. Have you ever just looked around and thought, why is everything such a mix? I mean, seriously, the coffee you're drinking, the sidewalk outside, none of it is pure. It's all this big, complicated, but kind of beautiful mess. And that's a fantastic question, right? You'd think it would be way easier if everything just stayed separate. A pile of pure iron over here, a cloud of pure oxygen over there. But that's not how it works. Nature, from the air we're breathing right now to the ground under our feet, seems to love mixing things up. So today, we're going to figure out why. So, here's our game plan. We'll kick things off by looking at the mixtures we see every day. Then, we're going to map out a sort of family tree for all of matter. And finally, we'll get into the really cool part, the secret social lives of atoms. That's where the answer is. Okay, let's jump right in. A world of mixtures. To get a feel for this, let's just look at a couple of examples you've definitely seen before. So check this out. On the left, we've got sugar dissolving in water. You stir it up and boom, it looks like one single clear liquid. But then look at the right. That's a piece of granite. You can totally see all the different little bits and crystals in there, right? Now, both of these are technically mixtures, but they are obviously very different. So what gives? To figure that out, we need a map. A way to organize all the stuff in the universe. It's kind of like a family tree for matter. And here it is. This chart shows the first major split. Everything, and I mean everything, is either a mixture or it's a pure substance. That's the first big fork in the road. Okay, so what's the actual difference? What makes something a mixture versus a pure substance? What's the dividing line? Well, it really all comes down to whether the parts are chemically combined or not. Think about it like this. In a mixture, the different ingredients are just hanging out together. They're in the same room, but they haven't actually changed. But in a pure substance, the atoms have chemically bonded to form a completely new thing. It's a whole new identity. And this actually takes us back to our sugar, water, and granite. The sugar water is what we call a homogeneous mixture. Homo means same. It looks the same all the way through. It's perfectly blended. The granite, though, that's a heterogeneous mixture. Hetero means different. You can easily see the different parts. It's chunky. It's not uniform at all. But, okay, saying they're just hanging out is one thing. How can we actually prove that something is just a mixture and not a brand new substance? Well, there's a classic experiment that shows this perfectly. Okay, follow this. First, you just mix some iron filings with some sulfur powder. Right now, it's just a heterogeneous mixture. And you can prove it, because a magnet will pull the iron right out. Easy. But now, watch this. You heat it up. You get this flash of light and heat. That's a chemical reaction happening. What you're left with is a new compound called iron sulfide. And here's the kicker. The magnet does absolutely nothing to it now. It's a whole new thing. And that's the key difference. Mixtures can be separated by physical means, but compounds, you need a chemical reaction to break those bonds. So that experiment really nails the what, but it brings us right back to the big question. Why? Why do atoms even bother doing this? Why don't they just stay single? And the answer is surprisingly social. The vast majority of elements are just not very stable by themselves. They're what we call reactive. You can think of them like little social butterflies. They're always looking to bond with other atoms to become more stable. Staying alone for them is actually an uncomfortable, high-energy state. And that right there is the fundamental reason our world looks the way it does. It's a giant collection of compounds and mixtures, because most atoms are constantly trying to bond and become more stable. This natural drive is what builds everything, from a tiny water molecule to a giant mountain. But of course, for every social butterfly, there is an introvert. There are a few elements that are totally fine being on their own. Let's talk about these lone wolves of the chemical world. So, who are they? Well, first you've got the noble gases. Think helium, neon, argon. These guys are chemically inert. They're already perfectly stable, so they have zero interest in reacting with anything. Then you have the precious metals, like gold and platinum. They aren't completely inert, they're just, let's say, reaction sluggish. They're chemical snobs. They're so picky about forming compounds that we can literally find them in the ground as pure nuggets. I love this cartoon. It really says it all. You've got this little helium atom kicking back, saying what translates to, thank goodness for the single life. And that's exactly its attitude. It is so stable and happy on its own, it just doesn't need to mingle. It is the ultimate introvert of the periodic table. So there's our answer. The world is a jumble because of the personalities of the atoms that make it up. Most of them are reactive socializers, always looking to partner up. And the few pure things we find, like gold or helium, those are the rare lone wolves who are perfectly happy being single. The big takeaway here is that all the incredible complexity we see in nature, it all comes from these simple rules about atoms wanting to be stable. And once you understand those rules, you don't just understand the world, you get the power to take it apart, to separate those mixtures and compounds. And that leaves you with a really interesting thought, doesn't it? If nature is all about combining things, and we've learned how to separate them, what amazing new things can we decide to build?